Good morning, or good afternoon, or good evening. This is Dr. David Cooper from the University of Central Florida. And one of the good benefits of having this CD is that you can watch it anytime you want to. What we're going to do throughout the CD is to go through the solutions to some of the problems. And I'm going to be focusing on the practice PE problems for those of you that want to see more than just the solution that's presented, which is often pretty abbreviated, but to see sort of the thought process behind it as well. However, occasionally we may slip in a end of the chapter problem or an example problem. And if it's an end of the chapter problem, it may be one that you've been assigned for homework, so there you go. You have a free answer given to you on this particular CD. So let's get started, shall we? I'm going to be focusing on the practice problems in air quality for the PE examination that is presented in the back of the text in Appendix E. And of course, the very first thing that shows up here is the ideal gas law, which all of you learned in high school chemistry, but which is certainly a massive tool for us in air pollution engineering. Air behaves as an ideal gas, and with this simple mathematical expression relating the pressure, volume, and temperature of an ideal gas to the number of moles, then we have a way to solve a great number of problems. All right, so the first problem is very simple. The volume occupied by 1 gram mole of an ideal gas at 25 degrees C in one atmosphere is most nearly. And you'll notice that the PE problems typically are worded this way so that you don't have to get an exact answer, but it's going to be rounded and there'll be enough separation that you'll be able to distinguish between the various choices. Now, you might simply just recognize the answer here. But if your memory goes back to high school chemistry, you'll probably recognize it as 22.4 liters, because that was the thing we learned, that 1 mole of an ideal gas occupies 22.4 liters at STP. Well, in chemistry, STP stands for standard temperature and pressure, but in chemistry, the standard temperature is 0 degrees centigrade. So we have to be a little bit careful here. In air pollution work, typically EPA writes regulations, and we typically talk about standard temperature of a gas, of air, as being at 25 degrees centigrade. So we need to find it at 25, and the method, starting with the ideal gas law, that will allow you to get that volume at any temperature is shown right here. The correct answer is C, 24.5 liters per gram mole. And we simply start with the ideal gas law and rearrange the components to give us the volume per mole, the desired quantity. And that leaves us with RT over P, substituting in the values for R, T, and P. And notice that we choose a value of R that is most convenient so that the units will cancel. We've got degrees Kelvin in the denominator and atmospheres in the numerator. So when we substitute those numbers, be sure to use absolute temperature in here. We come out with 24.5 liters per gram mole. Now, since I'm speaking to you from a studio with no audience, there's no questions that can be asked during this presentation, but I'll try to anticipate as we go some of the questions that might come up in your own minds and give the answers to those as we proceed. Okay, so for problem number 2, the ozone concentration at a monitoring site is measured as 0.11 parts per million at the standard temperature and pressure, what's the concentration in micrograms per cubic meter? The molecular weight of ozone, which is 3 oxygen atoms, is 48. And again, we're given 4 choices. We have to choose the most correct one. Well, this one you can't remember or guess at because there's nothing standard or common about this 0.11. So we have to actually calculate it. Here, the correct answer is C. And the answer can be derived from the ideal gas law. And for that, I refer you back to chapter 1 in your text, or you can obtain it directly from the equation in your text, which is simply 1,000 times the concentration in parts per million times the molecular weight divided by that volume per mole at 25 degrees C in 1 atmosphere. And that gives us 215 micrograms per cubic meter. If you were given the concentration in parts per billion, say 110 ppb, you'd simply divide that by 1,000 to get parts per million before you plugged it into this formula. Okay, problem 3. The SO2 concentration in a stack is 500 parts per million. Stack diameter is 12 feet, and the stack gas velocity is 65 feet per second. Gas temperature and pressure are given, and we need to calculate the mass emission rate of SO2 in pounds per day. The atomic weight of sulfur is 32, atomic weight of oxygen is 16. So again, we have our 4 choices. But now how do we go about this? Well, visualize the stack. With the gases flowing out at an average velocity, 65 feet per second. And the stack diameter is 12 feet. So we can easily calculate a volumetric flow rate of all of the gases going out, where Q is simply equal to the volume times the cross-sectional area, and the area is simply pi d squared over 4. Now that'll give us the total volume of gases exiting the stack, and we know that the SO2 concentration is equal to 500 parts per million, or the mole fraction of SO2, or the volume fraction, because they're the same, is simply 500 over 1 million. That would be the mole fraction of SO2, or the volume fraction of SO2. So as you can see, I think you can see we're headed to calculating the moles of SO2 leaving by simply applying the mole fraction to the total volumetric flow. And then once we have the moles of SO2, the molar flow rate of SO2, all we have to do is multiply that by the molecular weight, 64, to give us the mass flow rate of SO2. Okay, so you see how this is proceeding from our initial diagram. Q, given the velocity, we need the area. We can get that from the diameter. The mole fraction comes from the parts per million. The molar flow rate is just going to be equal to the mole fraction times Q converted using the ideal gas law into a molar flow rate total. So let's see the solution to that in numbers. And this is another way of looking at this with a partial volume and a volume fraction. So the parts per million and converted to a fraction is 0.0005, and that's a mole fraction or a volume fraction. So we can, in this approach, we're saying the volume flow rate of pure SO2, that is, if we were just to isolate the SO2 volume, would be 0.0005 times the volumetric flow. There's the velocity times the area, ID squared over 4, and converting seconds per day, because we're going to eventually need the answer in pounds per day. We get a volume of SO2 that goes out the stack of 3.176 times 10 to the 5th cubic feet per day. Rearranging in the ideal gas law to get the mass flow rate, and remember from the very first page we're given the ideal gas law, we can rearrange that. PV is equal to M over MW RT to solve for M. So if we're given P and V and molecular weight and T, we get the mass. And that's this rearrangement. M is equal to V times P times molecular weight over RT. And now we simply substitute the numbers in. Our volume of essentially pure SO2 times the pressure times the molecular weight of SO2, because we're not dealing with air or stack gases anymore. We've isolated the SO2 as a pure component, divided by RT, and T again must be an absolute temperature. Here we're dealing with units of degrees Rankine, so to the Fahrenheit measurement we add 460, and that gives us 32,800 pounds per day, which, by the way, is not an unusual SO2 flow rate for a large power plant. All right, let's move on to question 4.